ready to go live here. No, I just need to make sure that I'm not hearing us on the other screen. All right, I think we're good. So it looks like it's 12:30 on my time, so I'm gonna get us going. Welcome everyone to day 2 of Wisconsin Salt Awareness Week. I'm Allison Madison with the Wisconsin Saltways Partnership, which is a coalition of organizations across Wisconsin that's working to reduce salt pollution in our lakes, streams, and drinking water. So while it's fairly easy to deduce the fate of salt if you live near surface water or you see storm drains that are going to connect to nearby lakes or streams, it's sometimes harder for many of us to understand that salted pavements also connect to water that we cannot see, a groundwater. So I'm excited to introduce Ken Bradbury, state geologist and director of the Wisconsin Geological and Natural History Survey. I think I got that all right.
Yep.
So Ken studies the water that most of us don't think about too often, and he's gonna share some of his research with us today.
Okay, I'll go here and share my screen. Thank you, Allison, and hello, everybody. Are you seeing that, Allison?
Yep, you're good.
Okay. Well, good afternoon, everyone. I'm going to spend a few minutes today talking about salt in groundwater. And what you see here is a picture of a subdivision out east of Madison that I will, we've done some research there in recent years, and I'll be talking about that subdivision. So here you see somebody sampling groundwater in a rural subdivision. But I wanted to start by just telling everybody what groundwater is, in case you don't know, and give you a little background on the water cycle and why we care about this in salt in groundwater. So groundwater is the water that fills the pores, cracks, fractures, voids, and so forth below our feet. And if those rock or soil materials can transmit usable amounts of water, we call them aquifers. So here you see a typical Wisconsin landscape in cross section, and a few things to keep in mind is that water is beginning its cycle as precipitation, rain or snow from the clouds, landing on the landscape, and some of that runs off, and some of it enters the groundwater system through a process we call infiltration and then recharge. It becomes part of a groundwater system. And what happens to that groundwater when it gets below the surface? Well, some of it, first of all, it moves, and it will either move to a well, as you see on the left here, or it can move farther along a groundwater flow system and end up in a lake or a river or a wetland or something like that. The other thing you see on this picture are two different aquifers, a shallow aquifer and then a deeper aquifer. And this is fairly typical in most parts of Wisconsin, where we have two or more different aquifers. And so in my talk, I'll be talking a little bit about deep versus shallow aquifers. And it's important when we think about chloride or salt that's going to be transmitted in the groundwater as the groundwater moves. So it moves, it's a dissolved substance, so it's going to move with the groundwater. So it's going to move along these same kind of flow lines that you see the water moving along. Now let's give a little context to chloride in Wisconsin groundwater. Here's a map of the state that's produced by the UW-Stevens Point Groundwater Center, and they have this nice viewer that you can go on online, and there's the address to look at various constituents in groundwater that are taken from many private well samples that they have taken over the years. And so here you see averages of chloride in milligrams per liter by county, and most of the state is colored green, and that means that the county average is between 10 and 50 milligrams per liter of chloride. You can see that some of the northern counties have less chloride, and a couple of the eastern counties have more chloride, and that's probably because of geologic naturally occurring chloride in that water. So chloride is a component of salt, sodium chloride, which breaks down and dissolves into sodium and chloride ions. And I'm mainly going to be talking about the chloride ion today. As I mentioned, chloride is mobile in groundwater systems, which in scientists we call that conservative, meaning it doesn't get filtered out. It doesn't get it doesn't adhere to soil particles. It pretty much moves with the groundwater. So we call that a conservative contaminant. Makes a good groundwater tracer, by the way. Where does chloride come from? Well, I think if you're listening to this webinar, you probably know all this, but the main sources are road salt. And this weekend in Wisconsin, we saw an awful lot of road salt put on our highways. Other sources are on-site septic systems with septic tanks, and in particular water softeners, which use a lot of salt, and those often go into the septic system or the sewer system. Agricultural fertilizers on rural landscapes, potassium is often applied as potassium chloride, so there's a chloride source there. And we have other manure and cattle and hog manure and land spreading of sewage. And then we also have natural geologic sources, which are from evaporite beds of salt. Many of you may not realize this, but in the deep parts of eastern Wisconsin are underlain by some very, very salty water. And if you trace that over into Michigan, the deep groundwater under Michigan is really one of the saltiest places on Earth. So there are naturally occurring salt sources in the Midwest. As shown on the map, the background concentration in shallow groundwater in Wisconsin is something on the order of 10 milligrams per liter of chloride. Background, of course, is an interesting term because background when, was it before settlement or in some time in the past? But generally, I'd say that 10 milligrams per liter or less is a reasonable estimate of our background chloride. As far as drinking water, there is not a drinking water standard, a health standard for chloride, but there is a preventive action limit of 250 milligrams per liter, above which municipalities or the government are supposed to do something to mitigate high chloride levels. Again, this is maybe fairly common knowledge, but chloride and sodium concentrations have been steadily increasing in Madison lakes and in groundwater. And a lot of this information is found in these excellent road salt reports that the Dane County Public Health has been putting out every couple of years. This is data from the 220 road salt report. On the upper right, you see a graph of chloride concentrations in the Yahara lakes. And the point here is that those chlorides in surface water have been steadily increasing from when they first started taking readings back in the 1930s, and they've gone up quite a lot. Some of the lakes have gone up more than others. Lake Wingra probably the most, and that's probably because it's the smallest lake, completely surrounded by urban areas. Mendota has gone up the least, still gone up though, but it's the largest lake, so you would get the most dilution there. On the lower left here are chloride and sodium and chloride levels in groundwater in the Madison area. And here's where I've talking about the upper and lower aquifers. You can see there are 3 different time periods, 1978, 1998, and 2018. And on the left are wells, and these are Madison municipal wells that are finished in the upper and lower aquifers. And on the right are wells that are only in the lower aquifer. And so first of all, you can see that for both kinds of aquifers, the chloride has been increasing over the years, but it's done more in the upper aquifer than the lower aquifer because the upper aquifers are really more vulnerable. That's where the salt is going to hit first. And as a good example of that, let's look at well 14, which is over on the east side of Madison, between Madison and Middleton, along University Avenue near Spring Harbor and Lake Mendota. And chloride has been steadily increasing in that well for many years. And if you can look at the graph on the upper right, you can see that the chloride in well 14 has gone from something like 40 milligrams per liter in the 1990s to around 160 at the last time it was sampled. On the left in the map, you can see the location of well 14, which is right along University Avenue. These colored lines represent the groundwater capture zones, where the groundwater has come from over different time periods of 10, 15, or 20 years. And you can also imagine that all the salt sources there might be out by well 14. You've got University Avenue, you've got intersections with a lot of other city roads, you have a salt storage shed, and you have the lake there too. So there's many, many sources of salt out there in that well. And that's increased so much that I'm told that some people that use that water out there are actually starting to taste the salt. It's a big problem for the water utility because it's one of their best producing wells in terms of volume of water. So it's an important well, and yet the salt has been increasing there. So that's an example of a deep Madison well, but let's turn to the main topic today, which is shallower groundwater in a rural subdivision. And that's what I want to spend the rest of my talk discussing. We, being the Wisconsin Geological Survey, monitored a new rural subdivision east of Madison for over a decade. And the main object of this work was to find out, what does a rural subdivision do to groundwater when it's built? Does groundwater get better or worse, or what happens? So the focus was not necessarily on chloride, but chloride was one of the things we looked at. So that's what I thought I'd focus on the chloride data today. We also looked at nitrate, atrazine, viruses, and emerging contaminants, but I'm going to focus on chloride. So then the neat and I think a fairly unique thing about this study is that we examined some land where a subdivision was built, and we got in there before the subdivision was built, when it was still rural farmland. And so on the upper left, you see a photo of the site from 2001 when it was still a corn and soybean field, and you can see our little truck there in the middle. And then through the years, you can see how the subdivision was developed. Houses went up, and at the bottom in 2015 is pretty much like it looks today, although I think there are still some new houses being built out there. This is called Savannah Valley. It's a little bit east and south of Sun Prairie. So it's a typical Dane County rural subdivision. Here's another aerial view of the site. So on the left, you can see prior to development, we had this corn and soybean field, and then some woodlots and trees surrounding it. That's Highway 14 or 12 on the north side. It was in a corn soybean rotation with these interspersed woodlots. After some development on the right, you can see there's now streets there, a bunch of houses. These houses have have on-site sewer systems. In other words, septic tanks. There's no rural sewer system here, but they're all privately sewered. So you've got on-site septic systems, and of course you have suburban lawns, you have streets, and again the interspersed woodlots. So important change, and even, as I say, even more houses have gone in since this photo on the right was taken. We had a grad student named Jeff Wilcox who did a master's and PhD working on this site. And so this comes from some of his work. But here's a zoomed in air photo of the site with the roads and the houses and other information. The blue lines represent the water table elevation. The yellow arrows represent the directions of groundwater flow. The little orange spots represent places where we put in groundwater monitoring wells to sample, and I'll show you some of the sample results. The little green rectangles are sewage, on-site sewer leach field locations, so places where we would be introducing treated wastewater to groundwater. So these are the septic drain fields, and so the groundwater is flowing from east to west and a little bit north across the site. And you can see where a lot of these houses are. So let's look at some of the results. Well, first of all, a cross section through the site to show you the geology. So this is a cross section right across the middle of the Savannah Valley development. And so at that site, there's some shallow unlithified or unconsolidated glacial sand and gravel at the surface. And below that, there are a series of bedrock units, and you don't need to worry about the names so much, but some of them are sandstone, some of them are dolomite or limestone, and we have wells there. So the shallow monitoring wells that we drilled are really only going down into the water table. So the water table is the dotted line at the top here. Below that line, all the sediments are saturated with water, but above that line, they are unsaturated. So we are sampling shallow groundwater with most of these monitoring wells. But there are a few wells that are deeper. We call these the bedrock wells. So they're going down into these deeper aquifers here. And these deeper wells are really the wells that people in the subdivision are drinking out of. And I guess I didn't say this, but keep in mind that each of these homes has its own well. They are not on a municipal water system. So every house has its own well and its own septic system. So and the septic systems are up here near the surface. So let's look at the average trends in sodium and chloride across the subdivision. So this is the aggregated data from all the wells, but I've divided them into shallow wells, which are mostly up in that shallow sand and gravel, and deeper wells, which are down in the bedrock. And it's very interesting. First of all, you can see that there's a definite trend between the time when before the subdivision was built in around 2000, 2001 to our most recent samples, which were in 2013. There was a very steady trend of increasing trend in chloride of about factor of 3 from 40 milligrams per liter to over 100 over that 10, 15 years span. And the same with sodium, which you would expect to go along with chloride. In the deep wells, however, there was less of a trend, although we do see when we get in toward the end of our sampling period that the deep wells are beginning to rise as well. And that's not surprising because we have, you would imagine that it takes groundwater a while to move deeper into the aquifers and get down to those deep wells. So more impact in the shallow wells, less impact, but some impact in the deep wells. Little impact in the deep aquifer before around 2012. Now here are graphs from each well, and I don't mean to overwhelm you with data here, so you don't need to study any one of these in particular hard, but with particular detail. But look at the overall variation first of all, and I think this is interesting because it shows you that even over this fairly small site, there's quite a bit of variation in what's happening from place to place. And I'll go through a couple of these in a minute. But for each of these, at the bottom, on the x-axis, you've got the date of sampling, and on the y-axis, the chloride concentrations in milligrams per liter. And the red dotted line is the linear regression line. And the p-value is the significance of that regression. And if it's less than 0.5, it's considered significant. So any of these were less than 0.5, that's considered a significant trend. Here's one where it's 0.4, which is greater than 0.05. So that's not a significant trend. But you'll see that if you look carefully, a couple of these graphs are a little different, meaning they have a y-axis that goes to 400 rather than 200. So two of these wells, MW8 and MW6, the y-axis had to go to 400 because we had some very much higher chloride in those wells. And even though there was a lot of variation, the trends were at least at MW8 was a significant trend. MW6 was not a significant trend, but it was still high chlorides. And I'll talk in a second about where those are. But again, the point of this graph is to show you that chloride was generally increasing. In some, it was increasing from almost 0 to a very significant level. Others, it stayed very low and across this fairly small site. So let's look at how things varied from place to place. First of all, let's look at this one that was quite high, MW8, where we had a chloride that was over 400 milligrams per liter. Why might we see that here? Well, let's think about that. We've got a road intersection here of two highways. I would expect a lot of salt to be spread here. We don't have records of, exactly how much salt was spread, but this is a place I would have expected a lot of salt even before the subdivision was built. And indeed, we see a lot of chloride there. Another place we see chloride, although not as high, is down here at MW3. Now MW3 is again a well near one of the new homes, but this is a place that's down gradient of a number of septic tanks, and it's also down gradient of this road, which goes down a hill. So you expect that there's going to be salty road runoff as well as septic tank effluent getting toward this well, and instead we see a pretty steady increase from the beginning of the subdivision till the end of our sampling. In contrast, let's look at some wells that are farther away from things. Here's MW10 over here, kind of by itself. It's not particularly down gradient from a road, except for this is basically a driveway, may not get much salt. There's only one septic system in the area, and it hasn't had very much increase at all. It's almost zero chloride, as a matter of fact. So it's fairly pristine water compared to these other ones. And then another one that's interesting is MW1 down here, which has got a little more chloride, but not any trend. And again, it's a little bit away from the rest of the wells. It's probably getting a little impact from the septic system, which happens to be right south of the home there, but not a big trend. The other well, which was in the previous slide that had an axis that went up to 400 was MW6 right along the road here. And so this was a pre-existing county road that I think, again, would have gotten a lot of salt. It's downhill from the road down to the valley here. And so you would have expected road salt to run down here. So to sort of summarize what we find, and I didn't, usually I give this talk about nitrate, but again, this was not a nitrate talk, but we did find that nitrate concentrations actually decreased in this subdivision as it went from agricultural fields to rural homeowner subdivision. And that's because there's suddenly less nitrate fertilizers being applied. But in contrast, the chloride increased in most of the wells, as I've shown you. Some other things we looked at, atrazine, which is a herbicide used on corn, that decreased, which you would expect because they're not growing corn there anymore. And then we looked at some things like artificial sweeteners and human viruses that could only be sourced from septic effluent. And we did find those on some wells. So we are seeing septic effluent in the groundwater at low levels. We looked at a lot of other pharmaceutical compounds, and we really didn't detect any of them, which was pretty good news. So in summary, a rural subdivision has mixed impacts on groundwater. It makes the nitrate concentrations less, but it seems to have made the chloride concentrations higher. So we've learned that road salt and septic systems impact shallow groundwater because we've seen viruses, artificial sweeteners, and chlorides near septic fields and roads. As I just said, removing land from ag use reduced nitrate and atrazine, but it did leave behind some atrazine, low levels of atrazine, and increased our chlorides. I didn't talk about this, but we didn't see many pharmaceutical compounds. And I think you can see from the variation of the data over time that you really need a long-term monitoring plan to draw conclusions about development like this, because there were a lot of short-term fluctuations. And we've published this work. Here are a couple of articles in the journal Groundwater, and there have been a few others as well. The first is more about the background groundwater chemistry, and then the second article is more on the long-term monitoring. So I will stop there, Allison, and then answer any questions that have come in.
All right, and thank you so much, Ken. Really fascinating work. And yeah, I have some follow-up questions, but we'll take those from the audience here right now. So looks like one from Will has said, well 8 showed both increases and decreases in chloride from year to year. Do the decreases indicate chlorides being flushed from the groundwater?
I think that's probably true. Remember, groundwater chloride is a conservative constituent. So if you have say a big rainfall in the summer when we're not having a lot of salt, you could easily flush it through. It's a fairly permeable sand and gravel aquifer. So I think that explains some of those big swings in chloride in that well and in other wells.
So it would be flush, just to clarify, Ken, flush kind of from the surface aquifer or the shallow aquifer into deeper.
It could be flushed into the deep aquifer, or it could be flushed through the deep aquifer to a more distant, more distant discharge point. So that's an important thing about chloride is it will, if we turn off the source, it can go away. I mean, it'll out of the ground, it'll go somewhere else. It'll end up in the lake or the river or something, but it's not destroyed, but it'll move around.
All right, thank you. And then we have a question from Jane. Would a subdivision-wide septic, sanitary, and well systems rather than per house reduce the amount of chloride?
Well, I don't think it's going to reduce the amount of chloride because you're going to have the same load, per person or whatever, no matter how you handle it. But it would certainly change where it ended up. How you managed it and where you put the effluent. That's a question that comes up. Is it better for a small subdivision to have a unified sewer system or have individual systems? And here you get into a lot of questions of government questions. For example, a small subdivision doesn't have a government. Who's going to be in charge of this system? Who's going to pay for it? How does that all work? So those are not easy questions.
All right. So those are the only 2 questions we have right now. I'll wait a minute and see if anyone else from the audience wants to type in a question. But Jane's question is actually an amazing segue into our talk tomorrow with Kathy Lake, the pollution prevention manager at the Madison Metropolitan Sewerage District. MMSD is one of over 40 wastewater treatment plants in the state right now that are operating under a chloride variance because they are discharging fairly high rates of chloride into surface water. And the DNR recognizes there's no great way to deal with the salt that in large part is coming from the water softeners to the wastewater treatment plants, but also road salt can infiltrate sewer lines. So Kathy will be sharing a lot about her work and the work of the district around water softener. So yeah, I don't see any other questions right now. So thank you, Ken, again, so much. This was really incredible. And I hope that everybody is able to join us tomorrow for Kathy's presentation. And please do continue to share this link. It will be archived on YouTube. And yeah, look forward to the rest of the week.
All right. Thank you, everybody. Thank you, Allison.
Yeah.
Okay,
Bye.
Bye-bye.